Another problem: design a dog-legged stair for a public building. The columns are 230 mm by 230 mm. The floor to floor height is 3.60 and the live load on the staircase is 3.5 kilonewton per meter square and floor finish is 0.75 kilonewton per meter square. Use M20 grade concrete and Fe415 steel. The size of the staircase room is 3 meter by 5.20 meter. Now here we have to design the dog-legged staircase for a public building. The size of the stair room is given 3 meter by 5.20 meter and the floor to floor height is given 3.60 meter. The live load will be the 3.5 kilonewton per meter square. Floor finish is 0.75 kilonewton per meter square and the grades of the materials are we have to use the M20 grade concrete and Fe415 steel. So here the sigma value of the sigma CBC will be the 7 Newton per mm square and sigma ST will be the 230 Newton per mm square. So first step we have to calculate the design constant, which will be depends upon the grades of the material. That is, M is your modular ratio, which is 13.33, K is your neutral axis factor 0.29, J is your lever arm constant 0.90 and R is your constant for moment of resistance, which is considered as a 0.91. Now next step will be the calculation of the stair dimension. Here we have to design the dog-legged staircase. So we have to assume the two flights. So height of each flight is equal to floor to floor height divided by number of flights. That is, we are considering two flights. So after simplifying this one, we are getting the height of each flight is 1.80 meter. Then here the building will be the public building. So generally the size of the riser will be varies from 150 mm to 170 mm. So here we are assuming the size of the riser as 150 mm. So assume riser as 150 mm. So number of risers required for each flight is equal to height of each flight divided by size of the riser. So 1.80 divided by 0.15. So we are getting the 12 number of the risers. The next one, you have to calculate the number of the treads required. The relation between riser and tread is the tread is equal to R minus 1, that is rise minus 1. So number of risers are the 12 minus 1. So we are required the 11 number of the treads for each flights. So let us assume the size of tread is equal to 300 mm. So going will be your 11, that is number of treads multiply by size of the tread. So we are getting the going is your 3.30 meter. Now here you have to go for the arrangement drawing for this staircase. So size of the stair room will be given 3 meter and the 5.20 meter. So here we are assuming the clearance between these two flight as a 0.2 meter. So this clearance is considered as a 0.2. Then height, then width of the each flight is equal to, so this is the width of your first flight, which is equal to 1.4 meter, and width of the second flight is also considered as a 1.4 meter. So total this 1.4 plus 0.2 plus 1.4. So we are getting the 3 meter as a width of your stair room. Then from this side going will be your 3.30. Again width of the landing is equal to width of the staircase, which is equal to 1.4, and this remaining distance will be your 0.5. So we are getting the total from this point to this point, we are getting the 5.20. So this figure will be indicates the arrangement of the riser and tread in the given stair room. Then next one, we have to go for the calculation of the effective span. Here we have to go for the effective span for the first flight will be your this is your first flight. So first one will be width of the landing, that is 1.4, plus this total going, that is 3.30, plus width of the walls plus tread divided by 2. So we are getting this, after simplifying this one, we are getting the width for the first flight will be 5.08. Now you have to go for the effective span for the second flight. So second flight will be, this is your second flight. So width for the effective span for the second flight will be the this 1.40, that is landing, plus this going, that is 3 point landing 1.4, 3.30, that is your going, plus half of this wall plus half of this wall. So we are getting the 0.23, that is wall thickness is going 0.23. So it will be 0.23 plus this one, this landing again, that is 0.5. So this will be your first landing, this is your going, this is your wall thickness, plus again second landing, that is 0.5. So after simplifying this one, we are getting this effective span for the second flight will be 5.43 meter. Then we have to consider the step number 4 will be the loading calculation. Now before calculation of the loading, we have to calculate the thickness of the waste slab. Now let us assume that the overall depth of the slab will be considered as 40 to 50 mm for 1 meter effective span. So here we are considering the 50 mm is the overall depth of the slab for 1 meter effective span. So 50 into total effective span. So the here total effective span we are considering is 5.43. So 50 into 5.43. So after simplifying this one, we are getting the overall depth as a 271.5 mm. So it is approximately considered as a 275 mm. That is overall depth of the waste slab of the staircase. Now let us assume effective cover of 25 mm. So we are getting the effective depth as a, that is effective depth is equal to overall depth minus effective cover. So we are getting this D is equal to 250. Step will be the calculation of the loads acting on the staircase. Now let us consider 1 meter width of the staircase. So live load will be given as 3.5 kN per meter. Floor finish is 0.75 kN per meter square. Then the weight of the step is given as B into T into 25. That is unit weight of the concrete. The step can be, the weight of the step can be considering just like a slab having thickness equal to T. And this thickness T is given as the rise divided by 2. So here B is again 1 meter width. We are considering for the design. Our riser will be the 0.15 mm, sorry 0.15 meter. So divided by 2 into unit weight of the concrete. So after simplifying this one, we are getting the weight of the step as a 1.88 kilonewton per meter. Then weight of the waste slab is given as B into D into 25 into under root of R square plus T square divided by T. So B is again 1 meter we are considering. D is your overall depth of the slab, that is 0.275. 25 is again unit weight of the concrete. Then R is your 0.15, that is size of the riser, plus size of the tread, that is 0.3 square divided by tread is your 0.3. So after simplifying this one, so we are getting this self weight is as a 7.69 kilonewton per meter. Then we have to consider the total loads acting. First you have to consider the loads acting on the inclined part, that is the live load plus floor finish plus your weight of the steps plus weight acting on the weight of the waste slab. So after simplifying, after putting these values, that is 3.5 live load, floor finish 0.75, weight of the step as 1.88, and the weight of the waste slab is 7.69. We are getting the total load acting on the inclined part as a 13.82 kilonewton per meter. You have to calculate the load acting on the landing part. In case of the landing, we are not considering the weight of the steps. So we are getting 3.5 plus 0.75 plus 6.79. So total load on the landing part will be the 11.94. And for the design purpose, what we are considering the greater of these two, that is we are considering 13.82 as a total load acting and the 5.43 meter as a effective span for the design. Then the next step is we have to calculate the bending moment, which is given as WL square by 8. So 13.82, that is load, into 5.43 is your span square divided by 8. So after simplifying this one, we are getting bending moment as 50.94 kilonewton per meter. Now next step is we have to go for the check for the depth from the bending moment consideration. So bending moment is equal to R into B into D square. Bending moment is 15.94 into 10 to the power 6 Newton millimeter. R is your constant for moment of resistance 0.91. B is again 1000 millimeter. D is that value we have to find out. So after simplifying this one, we are getting the value of the D required. So this D required is equal to 234.40 mm. And what is the value of the D we are providing? We are providing the 250 mm. So D required is less than the D provided. Hence the design will be the safer side. Then the last step will be the calculation of the main steel and the distribution steel. The main steel will be calculated from the bending moment consideration. So this main steel AST is equal to area of the steel is equal to bending moment divided by sigma ST J into D. Now put up all the values. Bending moment as 50.94 into 10 to the power 6 Newton millimeter. Sigma ST is 230. J is your lever arm constant 0.9. and the D is your effective depth, that is 250. After simplifying this one, we are getting the area of the steel is 984.35 mm square. What is the minimum area of the steel required from the bending moment from the IS consideration? It will be 0.12% of B into D. Now put up the values. B is your 1000, D is your overall depth, that is 275. After simplifying this one, we are getting the minimum area of the steel required is 330 mm square. Now what is the area of the steel we are providing? We are providing the 984.35 mm square. So we have to provide the area is 984.35 mm square. Now let us assume 10 millimeter diameter steel bar. Then the spacing is given as spacing is equal to 1000 into area of the one bar divided by the total area of the steel we are providing. So this spacing is equal to S is equal to 1000 into area of 1 bar pi by 4 into 10 square divided by AST is 984.35. So after simplifying this one, we are getting the spacing as 79.79 mm. So you have to go for the lesser side. So we have to provide the 75 mm. And the next step, you have to go for the check for the spacing. The spacing should not be greater than 3 times effective depth, that is 3 into 250, that is 750 mm, and the spacing should not be greater than 300 mm. So we have to provide 10 mm diameter steel bars at 75 mm center to center. Then we have to go for the calculation of the distribution steel. So this AST will be from the AST minimum consideration 0.12% of B into D. Now after simplifying this one, we are getting this AST minimum, we are already calculating, that is 330 mm square as provided as a distribution steel. Now let us provide 8 mm diameter steel bars. Then the spacing is given as S is equal to 1000 into area of 1 bar divided by total area of the steel. So S is equal to 1000 into pi by 4 into 8 square divided by AST we are providing, that is 330. So after simplifying this, we are getting S is equal to 152.32 mm, so which is nearly equal to 150 mm. You know, to go for the check for the spacing, the spacing should not be greater than S is equal to 5 times effective depth, 5 into 250. So you have to provide which is equal to 1250 mm. Spacing should not be greater than 450. Hence we have to provide 8 mm diameter steel bar at 150 mm center to center. Then we have to go for the arrangement of the, that is reinforcement detailing in the staircase. So here this is will be your distribution steel 8 mm phi at 150 mm center to center. This is your main steel which is 10 mm phi at 75 mm center to center. This is your position of your column, that is 230 mm by 230 mm. This is your landing having width equal to 1.40. This is your passage 0.5 meter, and this is your going 3.30 meter.